Hey everyone, this is week 2, lecture 2. So in the last lecture, we had a very simple introduction to the concepts of linear regression. And this time, we're going to have a simple introduction to the concepts of hypothesis testing and confidence intervals, which are essential tools with linear regression for interpreting your results. Ready? Get your pens, and here we go. So as I mentioned previously, when we have a regression model, what we get out of it is, among other things, the slope coefficient, beta hat. And we just get one number. We get a point estimate. So in the case of the utility cost model, beta hat equals 4.79. And we haven't yet seen the formula for how you get 4.79, but we will. But in truth, the real value, beta, is probably not exactly 4.79, but hopefully it's somewhere in the neighborhood of 4.79. So what we need to do is figure out how certain or uncertain we are of this estimate. So I'm going to keep working with the example of the utility cost model. I'm going to add in another example, though, so we have one to compare it to. Suppose that we have a model of the price of used cars. Okay, so we've collected data on a whole bunch of used cars, and our model is that it is A plus B times a variable W plus an error term, and W equals the weight of the car in kilograms. So we've got sale prices, we've got W, and we estimate B hat equals 106, which means for an extra kilogram of weight adds $1.06 to the value of the car, or 1,000 kilograms raises the selling price by $1,060. So let's just imagine we had that regression as an example. Now, if you picture along a number line, what we're doing here is we have our point estimate, beta hat, but we also know that the true value is going to be in some neighborhood around beta hat. So it might be in a narrow neighborhood like that, or maybe it's in a wider neighborhood like that. And there are a couple of measures that apply here. So one is how confident we are that it's in this neighborhood. So let's say we want to draw a neighborhood that allows us to say we're 90% confident that the true value of beta hat is within this range. Okay, so we'll talk about how you do that. But now suppose that we want to be even more confident. Let's say, well, actually we want to be 95% confident. We want to find the range around beta hat that allows us to be 95% confident. Well, to be more confident, that means we need a wider range. Okay, so the size of the interval grows as the confidence grows. And the reason for that is the narrower the interval, the more likely it is that the true value is outside the interval. So if we want to draw an interval where we're very confident that the true value has to be inside that interval, then it's going to have to be a pretty wide interval. So in the case of the electric utility model, Well, we have beta hat equals 4.79. The way that we determine the width of these intervals is to use what's called the standard error of the slope estimator. The standard error of beta hat, which is the standard deviation, essentially, of our estimator. So let me just show you the numbers that are in the book. So there's the estimating equation, and these are the numbers from the regression model. And as you can see, well, once it comes into focus, you'll see. Let me hit the autofocus here. There we go. There we go. Okay, so in the second row there, you see the 4.79. That's the coefficient value. Next column over, the standard error. And that number is 0.13. So what's that number? Well, it's the standard deviation of beta. So the formulas that we're going to learn, what we estimate with beta is not just beta itself, but also its variance. And we can use the variance then to compute the standard deviation. And in regression analysis, the standard deviation of beta is called the standard error of beta hat. So once we have the standard error, and in this case, what did I say that was? 0.13. The standard error will determine how wide these intervals are. Now, there's an exact way of calculating it, but a very convenient rule of thumb to have in mind is 95% confidence interval equals plus or minus 2 times the standard error. Okay, and that is approximately. We'll make it more precise as we go along. When you draw an equal sign with a tilde over it, that means approximate. Approximately equal to. Okay, so then if we want to know how big these bounds are, so we've got a number 4.79. The upper bound would be 4.79 plus 2 times 0.13, and the lower bound will be 4.79 minus 2.13. And we would say that we're 95% confident the true value of beta falls in that range. And so the 95% confidence interval in the case of the utility cost model will be 4.53 to 5.05. Okay, so 4.79 minus 2 times 0.13 gives me 4.53. 4.79 plus 2 times 0.13 gives me 5.05. So that means what we've really estimated is an interval. Not just the slope estimate, but it's the whole interval. And the interval says, well, our best estimate is 4.79, but we're 95% confident that it falls in between these two numbers. So that is called a confidence interval. And remember, whenever you do a regression, what you get a best estimate, but equally important, you get a confidence interval. And you need to be mindful of the fact that if the confidence interval is very wide, your best estimate is not very precise. Okay, so what do we do with these pieces of information then? Well, we can engage in something called hypothesis testing. Hypothesis testing makes use of those point estimates and the standard errors and allows us to test certain possibilities, hypotheses. So with hypothesis testing, you begin, the jargon here is you specify a null. So for instance, for example, let's suppose there is no relationship between the price of the used car and its weight. Okay, I know I said that we derived a slope coefficient, but maybe in truth there is no relationship between them, and that's just random chance that we happen to estimate it. So when we've specified a null, then we have to state what that is in mathematical terms. So mathematically, the null is that beta, oops, no, I used B for that example. Just go back here. Okay, so mathematically, the hypothesis is B equals 0. And because this is the null hypothesis, I'm going to put a capital H here with a subscript 0. So when you see me write that, this is the null hypothesis. The null hypothesis is B equals 0. And then the alternative hypothesis, we'll call that H1. And the alternative is that B does not equal 0. This is the most common hypothesis that we test. We test this every time we do a regression. You run a regression, you get these slope coefficients, and the first thing you want to test is it possible that the true value of the slope coefficient is 0? And so to test it, what we want to do is assign a probability to that outcome, and then if the probability is low enough, then we would reject the null hypothesis. One of the ways of doing this, I'm going to explain two ways. They're actually exactly the same, but they're pictured a little bit differently. So one is to ask the question, is the value beta equals 0 inside the 95% confidence interval? Well, in the case of the utility example, let's look. So the 95% confidence interval is the range between 4.53 and 5.05. No, it is not. So beta in that example, beta equals 0, that is not in the 95% confidence interval. Therefore, we reject the null hypothesis, reject HO. And we conclude that beta hat is, we'll say it is statistically significant at 5%. Why 5%? Well, because we have a 95% confidence interval, so 5% is whatever's left outside there, which means there's only a 5% chance that anything outside the confidence interval could be the true value. So since there's only a 5% chance that a value of 0 could be true, given the estimate we have of the slope coefficient and the standard error, then we're going to say, all right, 5% is small enough that we're going to reject that possibility. Now, with the second example of cars and the weight of the car, So remember, we have beta equals 1.06. So this is the car example. And let's say that the standard error equals 0.61. Okay, so now the 95% confidence interval that is INT there. 95% confidence interval equals 1.06 plus or minus 2 times 0.61. Okay, so that gives us an interval of minus 0.16 up to 2.28. So this is a little different here. So now this spans 0. Okay, so that means the number 0 is inside 95% confidence interval. So that means we can't reject the null hypothesis. Can't reject the null hypothesis at 5% significance. So again, 5% here is just 1 minus 95%. So, and the jargon here means we've drawn a 95% confidence interval. If the number 0 is outside that interval, then that means there's less than 5% chance that that's the true value. But if it's inside the confidence interval, then that means that there's a greater than 5% chance that it's the true value. And so when we are using a 5% significance cutoff, that means if there's a greater than 5% chance that the null hypothesis is true, then we can't reject the null hypothesis. It may be improbable, it may be the probability is low, but it's not low enough. So what we want, if we're going to reject the null hypothesis, is we want to be able to assign a probability to it that's very low. And that how low we can set that probability, we call that the significance level. And in this case, we've chosen 5% significance as the cutoff. And in the case of the used car regression, because the number 0 is inside the 95% confidence interval, we can't reject the possibility that the null hypothesis is true. So in that case, we do not reject the null hypothesis. And another way of saying that is the relationship between the car weight and the price is not statistically significant. Okay, so WI is not significant at 5%. Okay, that is the first way of doing hypothesis testing, and now we can turn to the second way. Okay, the second way that we can approach hypothesis testing around regression results is using what are called test statistics. And this is actually going to be the more common way that we go about it. So a test statistic is we'll call it a score. It's a number that we calculate using the output of the regression estimation. So it's a score that follows a known distribution, a known probability distribution, if the null hypothesis is true. Okay, so stepping back a moment here, when we run the regression, we get beta hat, but I told you we don't just get the point estimate, we get beta hat plus its variance. And so in truth what we got is a distribution of values. Okay, so the distribution might look something like that. Beta hat, and it's very improbable that it's got a number way up here, and it's very improbable it's got a number way down there, but 95% of the probability distribution is located within 2 standard deviations of the point estimate. The problem is that we don't have the formula for this distribution. We don't know what the true distribution looks like, so we can't use beta hat itself. But it turns out we can take beta hat and its standard error, and we're going to call that SB. Okay, so for now we'll call it S with a subscript B. That'll be the notation. If we take beta hat and divide it by SB, this is a very common statistic. It's called the T statistic. The T statistic. Then, if the null hypothesis is true, T follows a known distribution. In other words, we don't know the shape, we don't know the exact distribution for beta hat itself, but the ratio of beta hat to its standard error, if the null hypothesis is true, it does follow a known distribution. Now, we've kind of seen this already, because when we looked at the first case of the utility model, so T equals 4.79 divided by, what did we say that was? 0.16, I believe. 0.16. Okay, that's going to be a pretty large number. In the car model, T is 1.06, and the standard error we said was 0.61. Okay, now let me just figure these out here. 4.79 divided by 0.16 equals, oh, that's a big number, 29.9. And 1.06 divided by 0.61 equals 1.74. All right, now, here's another rule of thumb. And we will make this more precise as we go along, but here's a rule of thumb. If the T statistic is less than 2, okay, and I'm thinking of the absolute value of the T statistic, so if that's a negative number, then T has to be greater than -2. But if the absolute value of the T statistic is less than 2, then beta is not significant at 5%. If T is greater than 2, then beta, sorry, that's beta hat. We're talking about the estimate here. Beta hat is significant. Significant at 5%. So T, in effect, is measuring how many standard errors is the number 0 away from our estimate of beta hat. Okay, so if 0 is located right there and the standard error is that amount, well then 0 is less than 2 standard errors away from beta hat. So in that case, it's going to be inside the 95% confidence interval, or alternatively, the t-statistic is less than 2, so its beta hat is less than 2 standard error steps away from 0. Now, hopefully that's clear. Now, we're going to be using these over and over. You'll get lots of chance to develop your intuition about how these work. One thing to keep in mind with the test statistic approach is if the test statistic is large, then reject HO. The test statistic is small, then do not reject HO. So a large t-value means beta hat is so far away from 0 that we can reject the null hypothesis. Alternatively, the way you can think about it is under the null hypothesis, in other words, if the null hypothesis is true, i.e., if, let's say, beta, if the true value of beta is 0, it is unlikely we will get t greater than 2. And because that's unlikely, if we do observe t greater than 2, then we're going to say, well, then it's unlikely that the null hypothesis is correct. And so we'll reject it. Now, let us introduce a related measure, which is called the p-value. The p-value is the lowest level of significance at which you could reject the null hypothesis. Okay, so let's say we've done our estimation here, and we'll say that this is the distribution of the t-statistic. So t-statistic distribution, and this is what we calculate. T equals, what did we get before? 29.9. Well, we've said that our cutoff was back here at 2. So 95% confidence interval, our cutoff would be anything greater than 2. Well, we got something way bigger than 2. So that means, so this would be the cutoff if we want to have a 5% significance level. But because we've got t equals 29.9, we could actually have a much smaller significance level. Or, borrowing our concept from before, 1 minus the p-value is the width of the confidence interval that excludes 0. So in this case, we could say, well, not just 95%, but a 99.999% confidence interval would still exclude 0 if we drew that out. But with the using a test statistic approach, using the t-statistic here, when we get a really large t-statistic, that means it's not just the 95% confidence interval, which is this part here, but we could make a 99.9% confidence interval, and the t-statistic would still be outside that range. So we can reject the null hypothesis at a much lower significance level. How low? Well, that's called the p-value. So if you calculate a p-value, let's say the p-value equals 0.002. Well, that means that you can say that the slope coefficient that you've just estimated is significant at the significance level of 0.002. And since that's below 0.05, since it's less than 0.05, then the coefficient is significant. Now, calculating p-values is somewhat complicated. The computer will do it for us. We'll talk about how the computer does it. But if we go back to this table 2.1 in the textbook, you can see that for the intercept, the coefficient value is 2.19. The standard error is 1.88. That's kind of a big standard error. So the ratio of the two is 1.16, and that's less than 2, so this is not significant. And the p-value is 0.25. So that's a high p-value. So that is greater than 0.05. P-value greater than 0.05 corresponds excuse me, to the fact that the 95% confidence interval encompasses the number 0. So the intercept in this model is not statistically significant, which actually kind of makes sense. That means that if the output of the utility was 0, there's a reasonable probability that the cost of running the utility would be 0. But when we look at the output variable, the coefficient is 4.79. The standard error is very small, 0.13. So the t-statistic, wait a second. Oh, I used 0.16. That's why I got a different t-statistic. So, but it's 0.13. So that means the t-statistic is 36.36. Divide 4.79 by 0.13, and you get 36.36. The p-value is very, very small. Okay, so the computer, as it says in the note here, that's 5.4 times 10 to the minus 67, which is very, very small. So we'll just say it's 0. And you can see that the 95% confidence interval doesn't encompass 0. We could draw a 99.999% confidence interval, and it still wouldn't be anywhere close to 0. So one point to take away from all of this is when you run a regression, you don't just get a point estimate. The point estimate's important. It's usually informative, but it's equally important to bear in mind you get a distribution of values for that slope coefficient. For the model coefficient, you get a distribution of values. And the more uncertain, the less precise that distribution is, the less confident we can be that that relationship it's measuring is actually non-zero. So next, we're going to have a look at another example of using a test statistic, and that is for looking at whether the regression itself has been informative. So I mentioned that one of the statistics that emerges from a regression is r squared. And the r squared gives us the fraction of the variance in the dependent variable that we're explaining using the model. It's the ratio of the regression sum of squares to the total sum of squares. Well, the r squared also follows a distribution. We have an estimate of what the r squared is, but what we actually have is a distribution. However, we don't have the exact distribution for r squared. But here again, we can transform it using a test statistic. So this time we're going to call it an F statistic. And it looks like this. In the case of the simple regression, That's a formula. N is our sample size. N is the sample size, and we take n minus 2, multiply it by r squared, divide by 1 minus r squared, and that gives us this statistic f. And our null hypothesis, remember we start by specifying a null hypothesis. The null hypothesis is r squared equals 0. If r squared equals 0, our model has no explanatory power. All we have is the average of the dependent variable. We haven't explained anything about the behavior of the dependent variable. The alternative is that r squared is greater than 0. Can't be less than 0 because r squared is always 0 or greater than 0. And so the logic again is going to be the same thing. If f turns out to be a large number, if f is large, then reject the null hypothesis. How large is large enough? Well, we have to use statistical tables to see whether it's large enough that there's less than a 5% probability that we would have got an estimate that large. Or alternatively, the computer package will compute the p-value associated with an f that size. And if the p-value is below 0.05, then that means we can reject the null hypothesis, and r squared must be greater than 0, which means we're actually able to explain some of the variance in y with our model. Okay, now, having introduced those two concepts, I want to go back now and talk about statistical distributions. So this should be a review concept, but we're going to be using these things all the way through the course, so it is important that we spend a bit of time now and get clear on them again. So let's just take a few minutes to go back over the concepts of statistical distributions and how they apply to regression analysis. Okay, now I've mentioned that when you run a regression and you get a slope coefficient beta hat, what you really have is a distribution. So, and I mentioned before the idea of the familiar bell curve. So the bell curve, we associate it with the normal distribution. The normal distribution. This, in the case of the standard normal, has a mean of 0 and a standard deviation of 1. So that means it's centered at 0, and the standard error, or the standard deviation, equals 1. I said that we can go 2 standard deviations up and 2 standard deviations down to encompass 95% of the distribution. It's actually minus 1.96 and plus 1.96. So that's why 2 is a rule of thumb. But in the case of the standard normal distribution, it's actually 1.96 times the standard deviation. And this, so if we go that far out either side, then this shaded area encompasses 95% of the distribution. And that means we've got 2.5% up here and 2.5% down there. So 5% in the outer tails and 95% in between them. So that's if we have a standard normal. So if you ran your regression and your slope coefficient was 0 and had a standard error of 1, then that'd be great. You can use the tables for the standard normal distribution. But that's never the case. So what we have to learn how to do is take the information in the regression output and turn it into a different test statistic where we do know what the distribution is. Well, that's what the t-statistic does. So the t-statistic is constructed so that if the null hypothesis is true, then the t-statistic will follow a distribution that looks like this. I'm going to have to change that one little bit later on as we go on. It won't be quite the standard normal distribution. It will be a related distribution that looks a lot like the standard normal. But for now, let's just say, regardless of how big beta hat is and how big the standard error of beta hat is, t equals beta hat over the standard error of beta hat follows the standard normal distribution. And I'm just going to add an asterisk. Almost. Okay. So one thing to have in mind in this picture is you got 2.5% in this tail up here and 2.5% in that tail down there. And so when we are looking at the relationship between the confidence interval and the p-values, we have to take into account the fact that 2.5% down there, 2.5% is up here. We'll come back to that in a little while. Okay, so that's a picture of the probability distribution. But in the case of r squared, remember we said we're going to construct an f statistic equals n minus 2 times r squared over 1 minus r squared. Well, the f distribution, the distribution of that statistic looks different. It looks something like this. Okay, so in that case, we're not looking at a symmetric distribution around 0. And so here, if we have 95%, and we have a cutoff where beyond that there's only 5%, it's all in one direction. Okay, there's no tails on either side. It's all in the one direction. So in this case, the decision that we make is if we calculate an f statistic and the f is up here in the high part of the distribution, then the probability of calculating an f statistic that large, if r squared was actually 0, would be so small that we reject the null hypothesis. So, just reviewing what we've done so far, we have confidence intervals. Typically, we think of a 95% confidence interval. And we think of asking, is 0 inside it? That's the first question we ask with regression outputs. If not, we can reject the null at 5% significance. And the null is the hypothesis that the relationship is actually 0, that there's no relationship between the explanatory variable and the dependent variable. Or we can construct a test statistic if the null is true, how small is the probability we would compute a test score at least this large. At least, missing letters here. At least this large. Okay, and if that probability is below 0.05, if it's below 5%, then reject the null at 5% significance. Significant, that's what that spells there. Kind of fell off the end of the page. And the p-value is the lowest significance level at which we can reject the null. So that is just a quick first pass over these topics. If it still seems confusing, don't worry. We're going to be going over these again and again throughout the course. You'll build up your intuition. It'll all click. It'll all make sense. Just make sure that you are keeping up with the reading in the textbook. Keep chugging away at the R tutorial because you need to be able to do these calculations on the computer. Believe me, you don't want to do them by hand and you don't want to have to use a calculator. So get good at using R, and next week we are going to move into slightly more complicated regression models. They're called multiple regression models, where instead of just having one explanatory variable, we are going to have multiple explanatory variables. So that will be next time. We'll see you then.